10. You recording?
Yes.
Yay. Let's, can you do me a favor, Henry? Pull the blinds on the left, just get a little more light. Yeah, there you go. That's it. And maybe get the other one too. No, on that. Thanks. Just get a little more light, but not too much light.
Oh,
wow. Okay, so we're on chapter 10, and we're learning about stars. 10.1. And one thing we're going to do in these next several chapters is we're going to start moving a little faster than we have before. So a lot of the stuff in the book, not a lot of the stuff, but some of the stuff in the book I'm not really going to focus on that much. So you need to try to pay attention in class and listen to what I'm saying, and that'll kind of help you guide your studies. Not paying attention. This would be good. Hey, those are stars. Each star is like our sun. A big ball of gas made of hydrogen and helium, just doing fusion in its nucleus, in its core, and giving off light. Imagine all these stars right here. Each one's probably got a system of planets going around it. We don't know that for sure, but most of the stars we can examine in detail seem to have planets around them.
Is this that picture you're talking about where they left it?
No, this isn't that. That's the Hubble Deep Field. And in that one, each dot was a galaxy, not a star. But this is stars in our own galaxy, the Milky Way. That's a star cluster is what we call that. All these blue stars are stars that were in about the same area. They formed about the same time. Now, one thing we can do is we can tell how far a star is away by parallax. Do y'all remember what parallax is? Parallax, hold your finger up in front of your face, and then close one eye and close the other eye, and do like that so it shifts to one side or another. Y'all know what I'm talking about?
Wow, that's so cool.
That's parallax. Isn't that great? It's the magic shifting finger. Now do it to my finger right here. Does it shift much?
No.
Because it's farther away. Okay? That's parallax. You can tell how far away something is by how much the picture shifts. And what they can do is here's our Earth going around the sun. They can take a picture of a star right here in January, and then take another picture of the same star in July, and see how much it shifts back and forth compared to the background stars that are very far away. And they can tell how far away the star is that way. Here's the way they do it. If a star shifts 1 arc second, do y'all remember that unit? Okay, here's the way arc works. This is 180 degrees, right?
Mm-hmm.
Are you with me, Caroline?
Yeah.
This is 180 degrees. Imagine 1 degree is about maybe that much, because you could go 180 times. 1 degree. A degree can be divided up into 60 units called minutes. So imagine that 1 degree divided up into 60 smaller units. Take one of those minutes and divide it up into 60 smaller units. That's arc seconds. Are y'all with me?
That's really small.
It's a really small amount of shift. Well, if a star shifts 1 arc second, when you take a picture in January of the star, and then another picture in July of the star, if the star is shifting 1 second of arc, it's 3.3 light years away. And they call that 1 parsec. 1 parsec is 1 arc second of shift. And And they know that distance is 3.3 light years. If it's shifting one little arc second in the sky when you take a picture in January and you take a picture in July.
Does it always shift?
Some stars are so far away they don't shift at all. If a star shifted exactly one arc second, it'd be 3.3 light years away.
Is 3.3 light years in the closest star?
The closest star is 4.3 light years. So there is no star that's that close. But if there were one that were 3.3 light years away, it would have one arc second of shift. If they're farther than that away, they shift less than 1 second. So all stars that we see in the sky shift less than 1 second. Yes?
Do they measure it in like 6 month periods then?
Yes. It takes 6 months to do a measurement. Because you got to shoot it in January and then you got to shoot it in July. You know what the closest star is?
4.3 light years.
How'd you know that?
She told me.
I told you that?
Yeah.
The closest star is 4.3 light years. 4.3 light years is the closest star, and you know what it's called? It's called Alpha Centauri. Well, Alpha Centauri is actually a system of 3 stars, and they're all rotating around one another. The Alpha Centauri system is 4.3 light years away. And let's see that on our... Oh, here's what it looks like in January. And then it shifts in July.
Whoa, that looks like a lot more than...
Well, it depends how good your telescope is. This is a real good telescope, so it's shifting. If that distance of that arrow is 1 second of arc, then that star would be 3.3 light years away. It's always less than 1 second, though, even for the closest star. So there's the Alpha Centauri system. This is what I'm trying to get y'all to make with your model, right? And when we finally get those done, we'll take a look at them. Because it's hard to tell from this picture exactly where the stars are. It's hard to make a 2-dimensional picture of 3-dimensional space. That's why we're making the model. But that's the closest star, Alpha Centauri. But it's actually, like I say, it's 3 stars. The Alpha Centauri system has 3 stars. And the closest star in the Alpha Centauri system, we call it Proxima Centauri. So the Alpha Centauri system is a 3-star system, 3 stars that kind of orbit around one another over a long period of time. Just kind of switch places. But the one that's closest to us right now is called Proxima Centauri, the closest one of that system. If you could travel at the speed of light, you would get there in 4.3 years. You can't travel at the speed of light. Only light can travel at the speed of light. So the light from Proxima Centauri hits our telescopes 4.3 years later. All the other stars are a lot further away. But you can see these lines that y'all are using. This line is 1 parsec from the sun. That line is 2 parsecs from the sun. That line is 3 parsecs from the sun. 3 parsecs is about 10 light years. But of course, the star isn't only out, it's also up or down a certain ways too. Y'all see what I'm saying? Are y'all with me? We call this the local group. This is our local group of stars. These are about the 20 or so nearest stars to us. You don't have to memorize all their names. The only ones that are really important are Alpha Centauri and Barnard star. Those are the only 2 we're going to talk about. How we doing? Y'all got any questions about this one? You like stars? No, y'all hate stars? What's wrong with y'all? Hey, there's Alpha Centauri. That's what it looks like if you look at it with a telescope and then leave the iris open. So you're taking in a whole lot of light. All these stars here are all background stars. That's Alpha Centauri. You wouldn't know it from any other star. It doesn't look any different. Where is it? Well, if you look at the Southern Cross, which is a constellation in the sky, it's kind of to the side of it. Well, where is the Southern Cross? It's in the Southern Hemisphere. You've probably never seen it unless you've been to South America or Africa, Australia. Anyone here been to South America or Africa or Australia? Did you see the Southern Cross in the sky?
Yeah, I did actually.
You did?
Yeah.
Nice. Well, you were looking near Alpha Centauri. Whoa. Were you impressed by the Southern Cross?
I guess so.
You were? You can tell me if you were.
I don't know.
Not really? I don't know. I've seen it. I saw it when I was in the Galapagos. And it was just another constellation, kind of like the ones I showed you last time.
When are we going back out?
We can go back out pretty soon. It's about to be a full moon. We got to wait until the full moon passes. And then we can go back out.
We cold.
Heck yeah. The seeing is always better in the cold, though, because there's not as much heat making the atmosphere move. You can usually see things better. Now, what about the stars? Are they moving? Or are they just still in space? Can you guess? Tell you what, 10 points, if you can guess.
But
Are the stars still, or are they moving through space?
Is it
Just take a guess.
off?
I'll tell you what, I won't even count off if you get it wrong. Are the stars just still, or are they moving? Just take a guess. Orange is correct. I won't even count off for this one. Peach correct. Purple correct. Blue correct. White incorrect. Stars are moving. All of them. They're all moving around. So if you look at a constellation like the Big Dipper, you know, all those stars are actually moving. But they're so far away that we can't detect the movement with our eyes. You know? If you're looking at a guy way across, real far away, and he's running, he's not going to appear to be moving very fast. Guy that's right next to you runs by, you go, whoa, Mr. Willis is fast. Guy real far away, you're going, is he even moving?
So wait, if these stars are like our sun, then they're suns that are moving. So why is that?
The sun is moving too. Our sun is moving.
Well, I mean, it's rotating, but
It's also moving through space.
really.
And the planets are just moving along with it. Yeah.
how far? How,
As a matter of fact, our entire galaxy, all the stars are in orbit around the center of the galaxy. Going like this. But the galaxy is moving too. Going around other galaxies.
Wait.
And all the stars are not equally moving at the same speed. Some are moving this way, some are moving this way, some are moving this way, but they all have a general movement around the center of the
What would
galaxy.
happen if a star hit another star?
Okay, then you could have some serious explosions. We're going to talk about that in about 2 chapters.
how far do you think our galaxy's moved?
Not very far.
It moves pretty fast, and there's a number in the book. I'm thinking it's 35,000 miles per hour. Our star, the sun, is moving through space in comparison to the center of the galaxy. I'll have to check on that number. So anyway, but some stars, not only are we going around the center of our galaxy, but some stars are moving in kind of strange directions. And the fastest one we've ever measured is called Barnard star. But take a look at that. See that point right there? See that star right there where that arrow's pointing? If you look at that star, that bright one there, there's a star there. And if you look at a picture that's taken many years later, look where it is now. See that where that arrow is? That star has moved from below that star to above that star.
Phew, that has to be light years, right?
That star is many light years away. And that distance, well, you can calculate that distance. Here's the Alpha Centauri system. We have calculated that it's coming towards us at about 20 kilometers per second. And it's going this way at about 24 kilometers per second. And if you know anything about physics, you can combine those two motions to get its true space motion, which is 31 kilometers per second this way. So, 31 kilometers every second. 31 kilometers is about how big St. Simon's Island is from end to end. So the Alpha Centauri system is moving about one St. Simon's Island per second through space.
Wow.
The whole system's moving. And any planets that are going around those stars are moving with them. But orbiting at the same time.
So how close are the three stars in that system?
They're pretty close together. They're probably, they're probably within a third of a light year from one another. You know the size of our Kuiper belt?
Yeah.
They're probably about that far from one another. I don't know the answer to that for sure. But for gravity to have a good effect on another object, they have to be pretty close. Once they get too far away, they aren't going to orbit one.
Has one of our satellites ever come close to running into a star?
No, all of our satellites just go around the Earth. And we have launched a few of them out there into space like Voyager. But they're still so close to our sun that they aren't even close to another star. It would take hundreds of thousands of years to reach another star. And the one we launched a few in the 1960s, it's been about 40 years, 50 years since we launched our first satellites that are just kind of flying through space. But they won't even get as far as as 4.3 light years. It would take them hundreds of thousands of years to get that far. So these stars are way out there. Now, the next part of the reading talks about brightness of stars. As you get farther and farther from a star, the brightness goes down. And it goes down by a physical phenomenon that is caused by the area increasing as you get farther and farther away. Imagine a certain amount of light coming out of this star that covers one square of area here. If you double the distance, the same amount of light will have to cover 4 squares. And if you triple the distance, that same amount of light would have to cover 9 squares. This is called the inverse square law. Have you ever heard of the inverse square law in any other class? Maybe they talk about it in physics or physical science? No? What this means is if you double the distance, you don't half the amount of light, you 1/4 the amount of light. If you triple the distance, you don't get 1/3 of the amount of light, you get 1/9 of the amount of light. It's the distance squared, the amount of light decreases by the distance squared. That's true of light, and that's true of gravity. Hey, you loud kids in the hall, you want to keep it down? We're trying to do class in here. There you go. It might be hard to understand this picture, so they got a little video here that I think is good. Inverse square law picture by Alan Sill. Thank you, Alan, for your work. And Stephen, don't forget about him. I already just told you that stuff. Okay, here we
Away from
go.
a point source, it steadily dilutes in intensity while spreading over progressively larger surface areas. The light intensity varies inversely as the square of the distance from the source. Gravitational attraction between two astronomical bodies follows a similar inverse square law for the same mathematical reason. This animation shows how the area covered by the light grows with the square of the distance and how light is spread out over that area as it moves from a point light source.
That wasn't very good, was it? So, what this means is the light's really going to drop off as you get farther and farther from the star because the light's having to spread out. The same is true about gravity. As you get farther and farther from an object, the gravity has to spread out and cover more area, and it gets weaker very quickly. The same is true about magnetism. If two magnets are real close together, the force is really strong. But as you increase the distance from the magnets, the force quickly gets a lot weaker. You've probably noticed that when you're playing with magnets. And they have to be real close together to really get the strong attraction. As soon as you get them pretty far apart, it gets progressively weaker. Fast. That's the inverse square law. So, real faraway stars are pretty dim. If we know how bright the star is, though, we can use the inverse square law to calculate its distance. If we know how inherently bright the star is, we can figure out how dim it should be. Here's a giant head in space. That would be scary, wouldn't it? And this giant head is looking at two stars. And she, is that a she? Mm-hmm. She sees the stars as the same brightness. Star A and B to her look the same brightness. Why is that? A looks dimmer than B.
Because B is bigger.
From where we stand, A is closer to her than B. So it's not as bright inherently. What we call the inherent brightness is B is a brighter star than A, but A is closer to her than B, so they look the same to her.
So does size have anything to do with it?
Size has something to do with it, and how hot it is has something to do with it.
So if A was bigger than B, then they could be like the same brightness.
That's correct. That's correct. Good thinking. So this is a problem we have when looking at a star and trying to figure out how far away it is. You can use parallax for close stars, but for faraway stars, they don't move any when you take a picture in July and you take a picture in December. Those stars really aren't moving any if they're real far away. So how can you tell how far away they are? You can't go just on brightness. It's tricky. There was a guy, what was his name? There was an ancient astronomer who set up a scale, Hipparchus. Hipparchus was an ancient astronomer who set up a scale that's called the apparent magnitude scale. And this guy didn't have a telescope, he just looked at the stars. And he said, oh, that one's about a 5 in brightness. And that one's about a 2 in brightness. And this was his brightness, apparent brightness scale, which we now call apparent magnitude scale. And what he said was that the brightest star that you could see in the sky, he'd give an apparent magnitude of 0. Alpha Centauri gives a 0. It's pretty bright. The dimmest star in the sky that you can see, he gives a number of 6. This guy Hipparchus. So this is kind of a weird scale. You're going to miss this question if you're not paying attention here when you take a quiz or a test. The lower the apparent magnitude, the brighter the star looks. That's opposite to what you'd think. It's a weird scale. The lower the apparent magnitude, the brighter the star. And he named it every star he could see in the sky, and he gave it a number from 0 to 6. 6 was the limit, the naked eye limit, the dimmest star you could see. You could barely see that star, he'd give it a 6. And if you could see the star really well, he gave it a 0. We now know that the brightest star in the sky, if you use this scale and continue it out in either direction as you use telescopes, the brightest star in the sky is called Sirius. It's in the dog constellation. And I haven't shown you this star yet. When we went out to the beach, it wasn't out, but maybe we'll see it next time we go. Sirius has an apparent magnitude of negative 1.5. That means it's even brighter than any star that was on Hipparchus' scale. And if you apply this to the sun's way brighter than all the stars that Hipparchus ranked. The sun would be a negative 26.7. The sun is the brightest thing in the sky. Do y'all agree with me on that?
Yeah.
Sun pretty bright? Go stare at the sun for a while and tell me if you agree. Don't stare at the sun. Y'all at home, don't stare at the sun. That was a joke. The full moon is negative 12.5. Venus, negative 4.4. Venus is the brightest planet, the brightest thing in the sky other than the full moon and the sun. And then, if you go in the other direction, with binoculars, you can see stars that are as dim as a 10 on the apparent magnitude scale. And the Hubble can see something up to 30 on the apparent magnitude scale. And so the apparent magnitude scale is just a rough scale. And the way it works is a difference in 1. So, see if I can find. So Alpha Centauri is a 0, and Betelgeuse is about a 1 on this scale that this guy Hipparchus set up. And if you work this out mathematically, Alpha Centauri is about twice as bright as Betelgeuse. A difference of 1 on the apparent magnitude scale is a difference of about 2.5 in actual brightness as measured with a machine. And if you just want to make it easy for you, difference of 1 is kind of double as bright. But remember, you're going down. The brighter stars are down here, and the dimmer stars are up here. That's the apparent magnitude scale.
And the 2 point, so for every 1, it's 2.5?
Every 1 point on the apparent magnitude scale is actually about 2.5 times as bright. They still use this scale because it was used in ancient times and it's been used going all the way up.
What's the guy's name again?
Hipparchus.
With an H?
Hipparchus. Hipparchus. He was a Greek philosopher. Yeah. Hipparchus. Now, that's what we call apparent magnitude. That's not how bright the star actually is. That's how bright it looks. How bright the star actually is a different thing. We call that absolute magnitude. Absolute magnitude is how bright the star actually is. Our sun in the sky is real bright to us because we're close to it. But if you actually compare the sun to other stars that we see in the sky, the sun's an average star. The sun's not way brighter than Alpha Centauri. The sun's just way closer than Alpha Centauri. Alpha Centauri and the sun are probably about the same brightness. We call that absolute magnetism. The absolute brightness is how bright the star actually is compared to all the other stars. Now, some stars are actually really bright compared to other stars, but our sun is not. Our sun is an average star. It's not especially bright. It's just real bright to us because we're so close to it. If you could pull Alpha Centauri and put it next to our sun, they'd be about the same brightness. And you'd be going, whoa, there's two suns, y'all. And you wouldn't be unlike Luke Skywalker at that point. Going, y'all, there's two suns. That's what he's doing right there. He's going, I wonder where my droids are. Now, see, he has the Force. So, it's very different from your life. You have no Force. You have to get along without being able to move objects with your mind. Which makes it tough. If you want a glass of water, you have to go get it. You can't just use the Force to bring it to you. Okay, so we're about out of time here. And that's all you got to read for tonight anyway. 10.1 and 10.2. Okay?